This lesson is titled Section 12-1. It is all about circles and some new things in circles called tangents, chords, and secants. There's also quite a few theorems in this section that talk about tangents and how they work with circles. Before we get started, we need to identify 3 new vocabulary words. First vocabulary word is chord, and a chord is defined as a segment whose endpoints are on the circle. Therefore, that means that it will touch the circle twice, and that segment will be in the inside of the circle. Second word is secant. A secant is a line that intersects the circle at 2 places. So it's similar to a chord in the fact that it touches the circle twice. It's also in the inside of the circle because it touches it twice. But the difference between the two is a secant is a line, a chord is a segment. A chord can only be a segment. A secant actually sometimes can be a ray or a segment or a line, and it normally goes through the circle. But the big key is the chord is a segment. The last one is tangent. A tangent is a line, ray, or segment that intersects a circle exactly one spot. That means if it touches the circle only once, it's on the outside of the circle. Because it only touches the circle once, you'll have what's called a point of tangency, and that's the point where it touches the circle. That point will also be on the tangent line, or tangent ray, or tangent segment. Now, to identify in a circle what the difference between a chord, secant, and a tangent is, let me show you. First of all, this is named circle H, because H is the center. You have radii HG, HE, and HD. You also have diameter DG, which goes across and through the center. Now, the difference between a chord, secant, and a tangent is this. The chords that are on this circle are the following. You have chord D, J. It touches the circle twice, and it's on the inside. You also have DG, which is the diameter. It touches the circle twice. It's on the inside, and it's a segment. And then you also have chord GF. It touches the circle twice, and its endpoints are on the circle. Those 3 are the chords. The diameter will always be the longest chord in a circle. Radiuses, or radii, are never chords because both the endpoints don't touch the circle. Only one endpoint on a radius touches it. Secants, there's only one secant in this picture. Secant has to touch a circle twice, and normally it goes through the circle, so hence it has to be a ray, a line, or a segment. But in this case it's a line, and we identify it with a line above it, and that secant is GF. So there is a difference between the 2 of these. You have segment GF and you have line GF. Line GF is a secant, chord GF, or segment GF is a chord. Lastly, you have tangent. Tangent is on the outside, it touches the circle once. Here's the tangent line, AB. Or you can name it AC or CB. And the point of tangency is C. So you have chords, touch a circle twice, they're in the inside and they have to be segments. You have secants, touches the circle twice, and then it normally goes through the circle, so most often it's a line. Tangent touches the circle once, it's on the outside. Point of tangency is where it touches that circle. Now with tangents, you have quite a few theorems that go along with circles. First theorem, called 12.1, and again, we don't care about the number. It says this: if a line is tangent to a circle, then the line is perpendicular to the radius drawn at the point of tangency. So in this diagram, you have tangent line AB, my point of tangency is P. P is also the endpoint of the radius OP. So because you have a tangent line at the point of the radiancy on the circle, then these are perpendicular. So line AB is perpendicular to the radius OP. That's a theorem. Now to apply that theorem to this page, we have circle O with radius OD. And in this drawing, you're also given the fact that DE is a tangent. So because you have a radius and a tangent at the point of tangency, which is D, you have a right angle right here. That's what that theorem says. A radius and a tangent at the point of tangency is perpendicular. So now I just have a right triangle, and I want to find this angle right here, x. So I just apply my three angles in a triangle equal 180. And if this angle is 90, then this angle that we're looking for is 90 minus 38, which is 52. So x equals 52 degrees. To apply the same theorem to that, just have a different drawing. You have circle O, and you have OL as a radius and ON as a radius, and it's also given that ML and MN are tangents. So radius OL and LM are perpendicular, so there's a right angle. Radius ON and MN are perpendicular because of that theorem. A radius and a tangent at the point of tangency is perpendicular. So because those are two tangents, I have two right angles. So now instead of a triangle in the previous example, I now have a quadrilateral. Well, I know 4 angles in a quadrilateral equal 360. So I can add up these 3 angles and subtract from 360 to find that angle right there. So if I take 90 plus 90 plus 117, I get 297. Then I'm going to take 297 and subtract that from 360, because 4 angles in a quadrilateral equal 360. I'm going to get 63. So that angle is 63 degrees. Here's my third example of using that theorem that says a radius and a tangent are perpendicular. So in my example, I have circle C, and my radius is CP, and my tangent is PT. My point of tangency is P, so this right here is my right angle. So now I just have a right triangle. Now what's interesting about this example is 20 is the radius. Well, CP is also a radius. So if 20 is the radius, then I know this radii is also going to be 20 as well. Now to solve for x, which is just this little piece on the outside, not the whole side, but just that little piece on the outside, I'm going to use the Pythagorean theorem. But I'm going to call this side y, and I'm going to use 20, and I'm going to use 21, and I'm going to find y. Then once I find y, which is CT, I'm going to subtract 20 from it just to get this little piece x. So to solve this, this is how I'm going to set it up. 20 squared plus 21 squared. Oops, that was a bad 20. It's a bad square. Let's try that again. Equals y squared. So I get 400 plus 21 squared is 441. When I add those two together, I get 841. And since it equals y squared, I have to take the square root of both sides. So I'm going to get y equals 29. Now that's a triple, 20, 21, and 29, that we don't use very often. But that means the whole side is 29. Well, if this piece is 20, I'm going to take 29 minus 20 and get 9. So in my problem, x is going to be 9, because 9 plus 20 gives me 29. Now here's a fourth example using that theorem that says a radius and a tangent are perpendicular. So in this circle I have circle O, my radius is OP, my tangent line is PQ, point of tangency is P. So that means this is a right angle. Now this problem is very similar to the other two, but there's a little bit more algebra involved. The radii in this problem are both x, so I'm still going to use the Pythagorean theorem to solve for x, but here's how I'm going to do it. I'm going to use x squared, which is a leg. The other leg is 15 squared. And the hypotenuse, this whole side, is going to be x plus 9. And I have to square that. So there's going to be some algebra involved in this one. But I'm still using the Pythagorean theorem, which is geometry. So I have x squared plus 225 equals the quantity x plus 9 squared, which means 2 of them. Now I'm going to have to FOIL that out, and that's an algebra skill. So the left side of my equation is not going to change for a while. That's 225. Let me write that again. Okay, now over on the right I'm going to get this. That's your first term, x squared. Okay, then your outside terms are 9x. Your inside terms, 9x. And your last terms, 81. So on the right-hand side, I get x squared plus 225. Again, I haven't touched this. On the right-hand side, I get my x squared. Now you can always, when you FOIL, remember what FOIL means, these two always combined. So my 9 and 9 are going to be 18x plus 81. Okay, so now I'm just going to bring my terms together. So if I would bring x squared to the other side and subtract it, what happens to your x squareds? They cancel. So now I get 225 equals 18x plus 81. I'm going to subtract 81 from both sides. And I'm going to get 144 equals 18x. Then I'm going to divide both sides by 18. And x is going to be 8. So that is what my radius is 8. Now look, when I plug 8 back into my right triangle, let me pick a different color to show you. I get 8, 15, and this whole side is 17. There's another triple. I have 8 plus 9, 17. That's how I solved for x. The second theorem they talk about in this section, theorem 12.2, and again we don't care about the number, is the converse of the first one. The first one said if I have a radius and I have a tangent, I have a right angle at the point of tangency. This just says the opposite. If my line in the plane of a circle is perpendicular to the radius at its endpoint on the circle, then the line is tangent. So now we don't assume that the line is tangent. We know we have a right angle. When we have a right angle, the right angle says that now I have a line that's tangent. So now in this case, the converse says this. Line AB is a tangent to circle O. So it's just the opposite. Before I had the radius and a tangent line, I knew the line was tangent, so I had a right angle. Now it says if I have a right angle, then I have to have a line of tangent. Point of tangency is still P. To apply the last theorem that says if I have a right angle with my radius and a line that looks tangent, then my line has to be tangent. So now I want to determine in this drawing if LM is a tangent line. I have circle N with the radius and L, and LM looks tangent, but now I want to prove to see if that's tangent. How you prove that's tangent is you prove that's a right triangle. Well, the right triangle is Pythagorean theorem. So I'm going to show that 7 squared plus 24 squared equals 25 squared, because 25 is a hypotenuse. So 7 squared is 49. 24 squared is 576. Sorry. 25 squared is 625. Now when I add these two together, I get 625. So because they're both equal, then I have a right triangle. Because I have a right triangle, then I have a right angle at the radius. So yes, LM is tangent. They also talk in this section about inscribed and circumscribed. So it's all centered around the circle. So when I ask what's inscribed in the circle, I'm talking about look at the object inside the circle and tell me which triangle is inscribed in the circle. And in this drawing, triangle RUN is a triangle that's inscribed in the circle. When they talk about circumscribed, they mean it's the triangle on the outside. So if I look at my circle, and it doesn't have to be a triangle, it can be any object. I'm just using triangles as an example. But if I look at the object that's circumscribed about the circle, in this case, it's triangle CAT. So think about inscribed, it means on the inside. Circumscribed, it almost looks like circumference. It's on the outside. So again, it can be any object. It can be a kite, it can be a quadrilateral, it can be a pentagon. It doesn't matter of the fact that it's a triangle. It just has to be a polygon. Inscribed inside the circle, circumscribed outside the circle. The last theorem in this section states the following. If two segments are tangent to a circle from a point on the outside of the circle, then those two segments are congruent. So here's what it's stating. I have point P on the outside of the circle. AB is a tangent and BC is a tangent. If these two are tangents to circle O, AB and BC, if they're tangent to circle O, and they intersect at a point outside the circle, then these two segments have to be congruent. So segment AB is equal to segment BC. That's what this theorem states. Now here's how you apply that theorem. I have a circle. It doesn't have a name because I don't have a center, but I have a triangle circumscribed about that circle. Well, that means that this line is tangent to the circle right there. This line is tangent right here. This line is tangent right here. Now I can find the perimeter of this triangle because I have that theorem that says these two are going to be equal, these segments are going to be equal, and these segments are going to be equal because of that theorem. So that means this. If this is 12 right here, then this has to be 12 right here. If this is 13, then this part has to be 13. And then the last part, if this is 8, then this part has to be 8. So now all I have to do is add my three sides. So I can do it a couple different ways. I can add this side 20, add this side 25, add this side 21. Perimeter is a distance around, so in this case it's the distance around the triangle. So when I add these, I get 66 centimeters. That's my perimeter. This is another example like the previous example, except instead of a triangle circumscribed about the circle, it's a quadrilateral. And right now, I have only 3 sides and I need the 4th side to find the perimeter. This side is 7, this side's 5, this side's 4. I need that side, and I don't have it. So to find that side, I'm going to apply that theorem and find these 2 missing sides. Okay, so I'm going to start here, and I'm going to say, well, if this is 4, then I know that piece has to be 4. Okay, to find this piece, I got to go all the way around the circle. So if this is 3, then this piece has to be 3. Well, if the whole thing is 5, then this piece has to be 2. If that piece is 2, then this piece is 2. The whole thing is 4, so that makes this piece 2. So the piece that's still missing is that little 2 there. So if I add them all up, I'm going to get 7, 5, 4, and my new side is 6. So I'm going to add 12 plus 10 and get 22 centimeters. That is my perimeter of the quadrilateral circumscribed about the circle. Now before you do homework, I want you to skip to the end of your handout to go to the part that says tangent lines with 2 circles. And this lesson is, what if I asked for how many tangent lines can I draw to 2 circles, not just 1 circle? So in the first example, I have 2 circles that touch right here at the point. I want to know how many tangent lines I can draw. Now these lines are not going to be straight, but I'm going to try my best to make them straight. In this first drawing, the 2 circles that touch at one point, I want to find all the tangent lines that are tangent. They don't have to be tangent to the exact point. So here's a tangent line that goes through those 2 points and touches right at that circle. Then you also have a tangent line out here. And again, these lines are supposed to be straight. It touches that circle there. That's the point of tangency. This is the point of tangency. So I can have a tangent line and have my point of tangencies be 2 different points. If I can draw one on the left, then I can draw one on the right. So in that case, I have 3 tangent lines that can be drawn, and they just have different points of tangencies. Now, if I had 2 circles that touch right in the inside, how many tangent lines can I draw to those 2 circles at that point? Again, that's supposed to touch a circle. There's only 1. Third example is 2 circles that touch and intersect at 2 different points. My lines of tangencies that I can draw, there's only 2. Again, these are supposed to be straight and they're supposed to touch a circle. So imagine that they do. There's only two lines I can draw that are tangent to those 2 circles. Now 4 is kind of interesting because they don't touch, but I still have 2 circles. So in this case, I can actually draw 4. Oh, sugar. Let me try that again. Here's 1. Again, that's supposed to be straight. Here's 2. That's supposed to be straight. There's 3. And there's 4. Again, the points of tangencies don't have to be the same, but there's 4 lines I can draw that are tangent to both of those circles. The last example, the 2 circles don't even touch. How many tangent lines can I draw? None. Now, begin your homework, which is on page 665 to 666. Thank you.